All right. Hi, everyone.
Hello.
It's really great to be here. It's so great to see that there's such a big community here that's interested in astronomy. I'm Samantha Scibelli. I'm going to talk to you today about what I do, which is identifying molecules in the depths of space with radio telescopes. And before I get into kind of the science of how we actually do this, I want to give a little background about who I am. So I grew up in upstate New York, not too far from here, yeah. So it was actually in high school when I got interested in astronomy, and there was a local astronomy club and an astronomy observatory in upstate in Albany called Dudley Observatory. And that's where I kind of got interested in astronomy. They actually gifted me an 8-inch Dobsonian, me and some other of the high school students that were a part of this group. So I have a strong connection to my own local kind of amateur astronomy organization. They're super important. And actually, at my high school, I was fortunate enough to be introduced to research itself early. So this is my research teacher. So we actually had a class on research. I worked with a local professor at RPI, which is Rensselaer Polytechnic Institute, um, and worked on a project there. And I was like, wow, I can't believe you can do this as a job. And so from there, I just wanted to continue on my path of astronomy research. I got my bachelor's degree in physics and astronomy at Stony Brook University in Long Island. Um, and I was dabbling in lots of different things. I actually did a project on like dark matter and how that's distributed in galaxies. So not at all what I'm doing right now. So it's okay for younger people in the audience if you change or don't know exactly what you wanted to do. I was super obsessed with dark matter and like light speed and parallel universes. So, but then I kind of switched gears. I moved across the country after I got my bachelor's degree to Arizona, to the University of Arizona in Tucson, and that's where I got my master's and PhD in astronomy and astrophysics. And when I got to Arizona and I saw those beautiful skies and the mountaintops with all these telescopes, I was like, I got to do observations. I need to look at what's really out there. And so, specifically, I got really interested in radio astronomy there. As you'll see, I'll show some examples. There's a dish out there. It's now a 12-meter radio dish, but it used to be a 36-foot telescope that was run by NRAO, which is where I work for now, run by the National Radio Astronomy Observatory. So there's a deep connection and deep history of radio astronomy out in the Tucson desert.
So you got away from light pollution
Yeah.
and then ignored light altogether.
Exactly. Well, I got away from water vapor too. So that was the key for radio astronomy is you get rid of water vapor up in that dry desert, and that's very important. Yes, exactly. Um, so then I came all the way back to the East Coast, and that's where I currently am now, the National Radio Astronomy Observatory. The headquarters are here just down the road in Charlottesville, and I've been there for about 3 years. And so that's kind of my trajectory and my path. Um, what do I do specifically? I use radio telescopes to study biologically relevant prebiotic molecules in starless and prestellar cores that will eventually form sun-like stars in order to trace their formation histories and to better understand our chemical origins. Now, you don't have to understand any of that. Maybe by the end of this talk, you understand what some of these terms mean, but I just wanted to give you kind of the punchline now and give you an idea of kind of what I do. So these are the instruments that I use in my research, these radio telescopes. This was me the first night of observing on Kitt Peak in Arizona, my first observing run in my PhD. This is me at a dishwalk. This is the very large array. So who has seen Contact? Right? So those are the dishes there. And then there's the new Apple TV show now that I have to tell people about, Pluribus. Who has seen that one? Yeah, so this is the instrument that did it, that contacted them and led to all the downhill, I guess. But anyway, so this is also run by NRAO, but they have the other headquarters out in Socorro in New Mexico. But mostly what I use now is the Green Bank telescope, which is not too far away, and you guys should definitely visit. I'm sure you have before, but they have a wonderful public tours. You can go up on the dish in some cases. You cannot walk on it like you can on these dishes, but you can gently tap it. And that's me up on a dish, I think last year or the year before. And so these are all my tools and how I actually explore the universe. So now let's get into kind of the science, right, of how do I actually do this? Now, to get everybody on the same page, I'm going to show where we're talking about in the electromagnetic spectrum, which I'm sure you've seen before, right? We have what our wavelength looks like as you go from long wavelength to short wavelength, and then as you go from low frequency to high frequency, depending on what units you're interested in. Now, when I talk about radio as somebody who looks at molecules in space, I'm actually talking more in this regime, something that you would consider microwave. Um, and so this is a few millimeters in length or sub-millimeter in length, and a few gigahertz, so 10 to the 8, 10 to the 9-ish hertz in frequency. And so that's the space of frequency range that I'm particularly interested in. Now, to understand why that is, pop quiz. No, I want everyone, it's pretty easy if you look at this figure to kind of figure out, but based on this, and maybe you already know this, but what determines the type of electromagnetic radiation emitted by astronomical objects? So who says it's A? Who says B? Who says C? Who says D? Okay, you guys all. Okay, this side of the room, you agreed? No. Yeah, it's temperature, right? And then it was given away right here. So not too hard to discern, but this is a really, really key aspect that I want you to take away. And if we're looking down at these low frequencies, you'll notice that we're actually probing objects that emit at cooler temperatures. And so just to kind of show off what I mean by this, I like this graph that shows kind of like the types of radiation, the temperature emitted by that object, and the types of sources that you can actually see. So for example, people come to you and talk about black holes and accretion disks. That's usually, you can see that kind of energy if it's really hot, really high energy, and gamma rays. X-rays can probe gas and galaxy clusters, supernova remnants, right? Ultraviolet visible is more like planets and what, and hot stars that we see with our visible light. And then as we go towards longer wavelengths, infrared microwave, this is when we're getting down to cold clouds of gas and dust. And so my specific interest is really in these cold clouds of gas and dust, these molecular clouds that will have these molecules in them and that are going to be forming sun-like stars, like I mentioned earlier. And these are at very low temperatures. So I have a scale here. If 300 K or Kelvin is roughly room temperature, then 10K is pretty cold. 1K is like negative 450 degrees Fahrenheit. Yeah.
You can go back 2 slides there.
Yeah, of course.
Right there.
Yeah.
So it appears you're saying that there's a relationship between the microwave wavelength and humans and butterfly. What is that supposed to mean?
Oh, the scale. Like we're a meter or so.
Oh, okay, got it.
Yeah, and a butterfly is like a few centimeters or something. So it's the wavelength. Just a fun way to illustrate the wavelength. But thanks, that's a great question. Yeah. Okay, great. Another way to illustrate this is to just show you one object that you can actually study in all different wavelengths, right? So this is like Whirlpool Galaxy. And if you look at hot gas, right, in the X-ray, you're only kind of seeing the center where you have that black hole accreting and emitting. And then your ultraviolet, you're only going to see the hottest, bluest stars. In optical light, you're going to see kind of sun-like stars. In infrared, you're going to see smaller, cooler, redder stars. But then in radio, it reveals something even cooler, if you will, the cold molecular gas. And we'll get into that specifically. And so all of these wavelengths can probe all different types of things in one object. My interest, yeah, of course.
Actually, what default colors did you need?
Yeah.
For radio emission?
This is false colors, yes. Yeah, so this is the CO molecule, and I'll show you exactly how we know that this is a CO molecule and what we're coloring it to. But it's just the intensity, and it just picked a rainbow scale. So it's the intensity of how bright this molecule is.
Which would be caused by the chlorine.
Yep, yeah. So you see more CO, which is tracing the molecular gas in the spiral arms of the galaxy. Yeah. Okay. Yeah, of course. Great questions, and keep asking them throughout. To show you kind of one particular example of the object that I study. So I mentioned in my first or second slide that I study starless and prestellar cores. That's what this is. This is a famous object, Barnard 68, which maybe you have seen before or have imaged some of these dense clouds. They look like just nothing in visible light, right? These are very dense, cold objects again. They're roughly 10,000 AU, which again, 1 AU is kind of an Earth-Sun distance, just to give you a scale. So there are many of these little things in molecular clouds, for example, in other galaxies, but mostly I focus on them in our own galaxy. So this is within our own galaxy. And they really just look like voids or silhouettes in visible light. Yeah.
Here they're a rare vacuum that we can produce here on Earth.
Mm-hmm.
What is the density of the atoms? Or so something like that go on.
Yeah, so it's per cubic centimeter, 10 to the 4, 10 to the 5. And compared to space, which is like 1 particle per cubic centimeter. So it's several orders of magnitude denser than space itself, comparing to that. Yeah.
Just a comparison, comparison. What is the number of particles per cubic centimeter, say, for a very good vacuum?
Well, you can get to very good like this type of pressure in laboratories now.
Like one.
I think so. Don't quote me on that. I'm not a laboratory astrochemist, but they can get to pretty low pressures. Yeah, for sure. Because there are experiments that do this in low vacuum. Okay, great questions. Yeah, but if we want to actually study and understand how dense it is really, because where do we get these measurements from, how dense and what's inside of them and what's the chemical composition, we need radio telescopes. So this is my fancy diagram of our radio telescope. But you can see now that once we go look at our space friends, oh no, I didn't like that. We see that our cloud is no longer empty, but filled with, this is thermal dust, and this is molecular gas. And this again is that CO molecule that I showed in the galaxy. But now you can see that shape where you see nothing invisible, where it's blocked out invisible, it's actually filled with this dense molecular gas, otherwise invisible. But our radio telescopes let us peer inside these objects because they are so dense and cold that really we need radio telescopes at these lower wavelengths to see these cold gas clumps. And so be able to see inside these dense starless cores, we need radio telescopes. Okay, great. Just another example going back to that same whirlpool galaxy image, but kind of a more zoomed in version. Basically, that's the same thing that I was showing, right? So like in the visible light, you see these dark dust lanes that look very obscure. This is where stars are forming. And you can see that the radiolite, the CO molecule, in particular, is tracing that emission here, which is cool, which is awesome. But how do we actually identify this as CO, or like what's going on? Because somebody mentioned this is a false color image. Like, how do we know what we're looking at? What's going on here? Or how can we tell which molecules are there? Because as I mentioned early on, my interest is looking for all kinds of molecules, right? Well, spectroscopy. So maybe you guys are familiar with this if you put, for example, like filters on your telescope. So this is a image of Orion Nebula. And as you are probably aware, people false color these images. And often what they do is sometimes do this by the composition, right? But this time that we're talking about atoms, people do this for molecules as well. So for example, red is your ionized hydrogen, green is your oxygen, blue is also another transition of your hydrogen, and they make this false color image, right? So for just as a reminder, this is kind of what is happening at the atomic scale. You have your hydrogen, you have here your proton, and there's an electron going around, and you have different energy levels. When an electron jumps down an energy level, a photon gets emitted, and that happens at specific jumps, and you can see it at very specific wavelengths. So if you see your emission at 600 and 50 nanometers, then you're like, woohoo, I've seen my H alpha line, right? So again, your gas of cold cloud of gas will emit your spectral line at certain wavelengths corresponding to the energy transition of that certain atom. And just in a very similar way, when we're talking about molecules, it's similar. And I'll go into the details of this. But this is what's very powerful about spectroscopy, is that it can give you a very accurate fingerprint of the chemical composition of your astronomical source. So maybe you've seen this as well. There's different ways to kind of view your spectrum. You have a continuous spectrum, the emission spectrum, like I just showed, where you're looking at a cold, dense gas cloud. And then there's absorption spectrum, where when you have a continuous light source going through your cold cloud of gas, then you actually see dips in your spectrum, or dark patches if you were to look at the diffraction. I think there are also arc lamps in here, maybe you've used before, where you're able to see kind of the emitting gas from like neon and argon lamps, and yeah, they're right out there. So it's the same kind of principle, right? And at the atomic level, you can think of it in the same kind of ways, right? So you have emission on the left and absorption on the right. Emission, again, like I said, you have your electron coming down energy level, photon is emitted. The opposite for absorption, you have an incoming photon being absorbed by the atom, and then you see basically a dip or a drop in your brightness in your spectrum. So just a little recap of spectroscopy. And this is, mainly what I think people think of when they think of spectroscopy. So when you look with like diffraction gratings, right, you see something like this, if we were to have our diffraction grating glasses looking at the light above. But you can put this into basically a plot where you have brightness versus wavelength, and this is what astronomers do. They take that kind of thing and they make it into a plot like this, like a spectrum. Yeah. And this is an absorption, just to show you an idea. But I'm going to show you lots of pictures of spectra, so I wanted to give you a breakdown of what this looks like. Yeah.
So these emission wavelengths you have here,
Yeah.
are they affected by the Doppler effect? Is there
Yeah.
something moving toward you or away?
Yes. Yes, they're affected by Doppler.
So does that mean you'll get a fake reading? You won't know it's 480.
Well, you should know if it is shifted, you can account for that. And then what you do is say, okay, our object is like 5 kilometers per second away or something. So yeah, usually you have an idea of the distance of your object, and you'll be able to correct for the Doppler effect. But good question. Okay, so that was just talking about atoms and looking in basically our visible light. Again, we're still in nanometers, and that's visible light. But actually, you can detect atoms and specifically molecules at all frequencies. So I've only been talking about electronic transitions, but remember, in visible light, that probes much hotter regions. So if we want to study our cool clouds of gas and dust, our starless or prestellar cores, we need to go to our longer wavelengths into our radio. And as you go to different regions of the electromagnetic spectrum, there are actually different ways you can do spectroscopy. So I've just talked about electronic transitions like the hydrogen atom, but there's also vibrational states and rotational states. And I'll talk specifically about each, but actually in each of these, you can detect molecules. One of the coolest things is that you can see small type molecules. This is CH, so carbon and hydrogen, CN, carbon and nitrogen, in the photospheres of stars. And actually, the first molecules ever detected in the interstellar medium were done in this method, using optical spectroscopy. So looking at the star, and then there's gas kind of in the photosphere around the star. And so that's why you're seeing absorption lines here and detecting those molecules. So pretty cool. And they also detect some metals like titanium oxide as well. So that's pretty cool. But really, you can only study molecules like this for really hot things like stars. So we can try to go to a little bit longer wavelength, and that's in the infrared. And that's vibration, which is cool. So if your molecule, like this is water that I'm showing here, it has your H, your two H's and your O, and they can move like this, or they can move like this, or like this. And they have different ways of stretching, basically how the atoms move. And that will determine what type of energy gets emitted for you to be able to see in your spectrum. And what I'm showing here are different modes. It's kind of hard to see here. I'll show another example. But what often happens, this is for C2H and HCN, they have very similar movements. So a lot of molecules, if they're structured similarly, they can both move like this, and it's really hard to distinguish between individual vibrational modes and to actually be able to identify individual molecules. And where this comes up particularly is if you've seen observations from the James Webb Space Telescope. A lot of the observations there are in the infrared. And what they do is they look at vibrational states. And this is an example of infrared spectra of a star-forming core. But you can see some of these observations also suffer from these overlapping vibrational modes, where you have multiple molecules where you can't really tell which one you're looking at, because you could be looking at multiple things kind of mixed together. Okay? Again, you don't have to know all the nitty gritty of this, but I just want to mention all of this to you. Yeah.
This whole left into this here.
Yeah. Yes, that way. Yep. Yeah. Yeah. So the sensitivity drops down here by quite a bit. So this is noise level here. So yeah. Okay. But what I want to argue with you all and what I want you to take away is that radio is the best. That's the main point of why I wanted to tell you all of this, is because in the microwave, basically, or in the radio submillimeter, we don't have to worry about we don't have to worry about the stuff that we have to worry about with the other things. Basically, because you have a molecule, your molecule is very unique in terms of mass now. So because you have a carbon atom and say an oxygen atom in the case of CO, they each have their own masses. And so when they rotate, they have a very specific angular momentum and moment of inertia. And this is unique for each molecule. And this moment of inertia and this angular momentum, that will release an energy, just like it kind of in a similar way as the electronic transitions, as when it rotates, it is released in quantized packets or different energy levels, but this time of rotation, and it happens very specifically, and it's only for that molecule with that mass. And so you don't get the same thing of the overlapping modes that you do in the infrared, and you don't have to worry about having to look at some super hot source in order to see anything in your electronic transitions. And so rotational states are really, really powerful because they let you unambiguously identify your molecule with great precision. But we need to care about all the other things, because actually electronic states have vibrational and rotational structure, and vibrational states also have rotational structure within them. So we need to understand everything, but I'll just say rotational states are really what I'm focused on and what you should be taking away from this as the most powerful tool, I guess, to unambiguously identify your molecule. And I'll show a specific example of this now. So the first, actually, the detection of molecules with this rotational spectroscopy method was done at Kitt Peak in Arizona, the same place that I did my thesis work. It's not the same telescope, but it was that NRAO 36-foot. So again, this connection here. And what they did was that they were able to know, based on the mass again of the CO molecule, and do some calculations to see that it has these types of rotational transitions. And if they go to the lowest rotational transition, that occurs at exactly 115 gigahertz or 2.6 millimeters. So if they tune their radio telescope to this exact frequency, and if they saw emission, then they were like, huzzah, we've seen CO. And look what they did, they see it. So this is from their actual spectra from the 1970 paper, and this is the first detection of CO, this 1-to-0 transition towards this source Orion KL, nearby star-forming region. And so this was really the birth of being able to detect molecules in space via this rotational spectroscopy method in the radio regime, or in the millimeter regime, because again, this is at 2.6 millimeter frequencies. And you can see here the Orion Nebula in visible light and how different it looks when you look in radio. So the grayscale, which might be a little hard to see on the projector, is CO. And there's another molecule here, N2H+, that traces a bit of the more denser gas here. We're going to get there. Yeah, I'll get to that. Yeah. But here's another view. But what I want you to take away from this is, again, this is Orion Nebula. I love this picture. Again, you know, radio telescopes also have cool pictures. This is actually, the orange is false colored to ammonia, so NH3 here. This is what the spectrum looked like at one of the points along here. And this is what this is false colored as, and there's infrared dust in the blue scale.
For clarification, are those images of the exact same piece of cotton?
No, no, these are not. The previous one was, oh, sorry, I think I am not sharing anymore. Should be able to see it now. The previous one was, oops, this one.
Yeah, those are the
Yes.
extra.
Yes. Yeah, but this one is not. But basically what I want you to take away from this is that radio telescopes are extremely powerful probes of cold, dense gas and of molecules, because we can unambiguously identify them with this rotational spectroscopy method.
Your image is clear. That was done by a single dish, but by an array.
This is a single dish. This is the GBT. This is Green Bank, but we had to do many mapping observations. Yeah. Yeah, this is the Green Bank. So that's props for Green Bank. Okay. Now let's get into the fun stuff. Now that you kind of understand the background of what I'm actually doing in the spectroscopy. let's talk about what other molecules you can think of. I've mentioned a few, but I just so everybody's on the same page about what I mean by a molecule. Basically, these conglomerates of atoms together, right, put together by different chemical forces. But what other molecules that I haven't mentioned already can you think of from your, say, everyday life? Amino acids, methane, somebody said, I think. Yeah,
Organic one.
organic molecules, exactly. Yeah. So, yeah, PAHs. Yeah, so again, they can be more simpler ones like O2, but we can get up to things like DNA, caffeine is a good one. Yeah, so we can build up these molecules, and what a lot of people have been trying to do is to kind of test this limit and see how much of these molecules or how big we can really go. So how many molecules do you all think have actually been detected in space so far? So 40, 140, 340, 640. I'll just let you guys fill that out. Okay, well, the D. Okay. Everyone have their answers locked in? Okay. Okay.
Devin says E.
C. Okay, well, so this number has actually like grown since I used to do these when I started, well, when I gave my PhD defense talk 3 years ago, we were at 260. So it has really grown, and I'll show you an image of that. And this table is from just like the end of last year, and it's already like 40 molecules out of date. But what's shown here is kind of like all the different molecules grouped by number of atoms. But you can see there's a lot of species, a lot of diversity of types of molecules that have been detected so far. I will get to that. Yeah. But it depends who you ask. If you ask a chemist, they're like very few. But if you ask an astronomer who thinks anything higher than helium is a metal, like everything is. But so here I'm showing kind of this exponential growth, right? So here is the number of detected molecules on the y-axis versus year. And you can see things really started to pop off with the CO detection with the NRAO 36 foot. And you have these growth spurts actually every time you have a new telescope coming online. So you have a 36 foot, you have the IRAM 30-meter dish, which is in Spain, the Green Bank Telescope in West Virginia, and the Yebes 40-meter in Spain. And these are all what are considered single dish telescopes, which somebody has already mentioned, where you have a single dish looking at kind of one field of view on the sky at a time. All of these telescopes I use in my own research, and so this is me at each of those telescope sites. So it's fun that I get to show that off. So these telescopes are great. But you'll notice there's another observatory that comes online a little bit later, ALMA. So who's heard of ALMA, the Atacama Large Yeah. So this is what's known as an interferometer. So you have multiple single dish telescopes coming together to act as one larger telescope in order to see finer detail and to improve sensitivity. And I like to show off kind of what that looks like in one example. So this is observations. Again, this is our fun spectra or fingerprint of different molecules in the radio regime. The top is a spectra towards this carbon-rich star IRC 10216 with the single dish telescope with the IRAM 30-meter in red. And then the observers, they did the same exact thing, the same amount of time, same region of the spectrum, same position, and looked with ALMA. And you can see that there are many more of these squiggly lines or our fingerprints of basically new molecules that have popped out of the spectrum.
Where'd that go?
Yeah, I think
Yeah.
basically this is, I think here maybe, or this here.
This is nicely lined up. Everybody's nicely lined up. So that out there.
Yeah. Because you'll notice too, like the scales, the y-axis are very different because this is zoomed in. So maybe something was going on there that is now no longer. But that's a good question. But you basically have many more of these U lines, right, which are actually unidentified, and that can be followed up to try to figure out what they are, which is very, very cool.
Let's go back to the one that showed all the various, uh, molecules, yeah, this one here. I see some aluminum. I'm wondering why. I guess there's more aluminum. Okay, I see it now, yeah. I was just wondering if there's a particular reason why there is a greater incidence of some of these other things rather than aluminum or potassium, whatever.
Yeah, I mean, if we think about cellular evolution and what gets spit out, carbon, everything, carbon, hydrogen, oxygen, nitrogen. Yeah, so only in very kind of particular environments do we see the metals. Yeah.
Rich wants to know if chocolate's good that.
Chocolate. Wow. I don't think so. I wish. Yeah. Caffeine, well, not caffeine yet. I think there is an astronomer who wants to. We need Dunkin' Donuts to buy in or something, but exactly. But basically what I want you to take away from this diagram is that 90% actually of molecules detected in space have been identified by radio telescopes. So that is another reason why there's such a deep connection between me, a radio astronomer, and molecular astronomy, or what's now known as astrochemistry. So this really birthed this new kind of field of astrochemistry or molecular astrophysics, which is the study of the formation and destruction of molecules in the universe, their interaction with radiation, and their feedback on physics in the environment. And this is, again, all of these squiggly lines are, each of them is a different molecule or different transition of a molecule. And so we really have a lot to work with here, and we have a lot of things to explore in many different types of objects. And so I really like this quote also by Eddington. He says, I write about molecules with great diffidence, having not yet rid myself of the tradition that atoms are physics, but molecules are chemistry. But the new conclusions that hydrogen is abundant seems to make it likely that the above mentioned elements, hydrogen, oxygen, and nitrogen, will frequently form molecules. So we had physicists even in the 1930s really scared and worried about molecules, and that they're going to have to, understand these things and use it for physics. Which turned out to be true. And so it's not just physicists. Yeah.
Like, for instance, especially in reference to that quote,
Yeah.
maybe not hydrogen, but let's say carbon and oxygen. What fraction of carbon in the universe is just atomic carbon?
Yeah.
Molecular carbon. And,
yes.
And for other atoms as well. I was trying to, are most of carbon atoms bound up in molecules? Probably not.
No, that's not there. So it's hard to get an estimate though, because we can observe so we can observe CO very easily. There is people trying to understand what's considered the CO, like CO dark gas, if you've heard of this, where you can observe like ionized carbon structure in like the infrared, and to be able to try to pin down exactly how much of this ionized or neutral carbon there is out there. But it's much more difficult to directly observe. So it's kind of hard to say. But hydrogen itself is much more abundant compared to all of these, orders of magnitude more abundant. And neutral hydrogen and ionized hydrogen are more abundant than the molecular hydrogen.
So maybe you go into this, but what is the usual mechanism that molecules get formed? Just random collisions in space and it's a common species.
Yeah, it's a lot of, so you would think that they wouldn't, but they do. And so it's a lot of two-body reactions. They have to be exothermic. They have to be like very particular ways to do it, but it's possible because you have this spontaneous kind of, they go over a barrier and it can happen. So yeah.
Presentation a year or so back, on covering protoplanetary disks using ALMA.
Yeah.
Have you peered inside those protoplanetary disks?
Yes. Yeah. I'll show an example of that actually. Okay.
Quick question.
Yeah.
So in a star, the temperature is like in our star, little star, 15 million degrees. Are there any molecules in the star? Oh, I mean, that's not a good example because it only got hydrogen and helium, but.
Well, in the photosphere of some stars, you can see molecules, like I was showing earlier in the electronic states. Yeah. Yeah, similar temperatures, tens of thousands of Kelvin.
Okay.
But it's very rare to see that. And usually you're talking about, I guess maybe cooler stars as well. Like maybe 5,000 Kelvin for like some brown dwarf M-type stars. Okay, so astrochemistry is not just exclusive to chemists and physicists. It's very interdisciplinary. So there's chemistry, planetary science, engineering, and often you can think of it in kind of three pillars. So today I'm just focusing on observations. So being able to detect these molecules in space. But there's also, perhaps more importantly, are these other pillars. For example, laboratory data. So how do we actually know which frequency that I'm looking at is assigned to what? Well, we need laboratory spectroscopists to go in and to measure the actual frequencies in the lab. And so this is really, really important. It's not something I do, but I use the tables that they calculate for my work. And then we have theory, which is kind of what you were discussing, like how are these molecules actually forming? What are the mechanisms that they do that? And all of these things. So this all is important. And I just want to mention that to give you an idea of how broad astrochemistry can get. And so there's some people that, yeah, just do some of these. I focus mainly on observations. I do a little bit of theory, but I won't get into that really today for the sake of time. But what I am interested in, which is what I think that you guys all came here to kind of talk about, is that I'm really interested in some of these molecules that are kind of the precursors to prebiotic chemistry. So in astronomy, the literature, the people kind of talk about COMS, which are complex organic molecules. So this is anything with a carbon atom and at least 6 or more atoms. And so I've kind of highlighted what those boxes are. And we're not saying that these are sources like signs of life by any means, but what we're saying is that these molecules are important for life on Earth and they're important for building up larger things. So they are the precursors to building up, say, amino acids or DNA or RNA and things like this. And I'll show examples of that. So for example, methanol is the kind of alcohol you do not want to drink. Acetaldehyde is in a lot of fermented foods and wines. It builds up in your liver and gives you a hangover if you drank too much. And glycoaldehyde is a very simple sugar. And so all of these things have been detected in space and are some molecules that I specifically am interested in looking at. And new molecules are actually, I mean, as I've shown, continuously being added. This is another complex organic molecule detected with the Green Bank telescope. This is a sulfur species. This is the sign of it right there, it's spectral fingerprint. This is another fun one. I don't know if anyone has heard of dimethyl sulfide in the news. Okay, so this dimethyl sulfide was thought to be like a bioagent in a exoplanet atmosphere, which we can talk about why that was crazy in and of itself, but it's also detected in this high mass dark cloud in the center of our galaxy. So there are different ways to produce it, let's say. And so it's not just exclusive to places where there is life. This is also, being able to understand what molecules form in the cold depths of space can kind of put our things into perspective when we think about what can actually be, for example, a biosignature. But one of the interesting things too, if you look, what I'm showing here is that today most new molecule detections come from these dark clouds, like the one I just showed where the dimethyl sulfide is. So this is breaking up the detections of new molecules based on type of source. So blue is star forming region, the green is dark cloud, orange is carbon star, pink is other, and red is like a line of sight diffuse cloud. And so you can see compared to even a few years ago, most of the new detections are actually coming from this dark cloud region. And so this is another reason why I'm interested in looking at these dark starless clouds. So when I talk about that, this is kind of our picture of the molecular life cycle. Just to put us all into perspective, I'm focusing mainly on the dark cloud stage before there are stars forming. But there's a rich chemistry throughout. So again, you can see these types of chemistry in the stars, in the red giant phase, planetary nebula, for example. On the massive end, you can also see them. But what my interest is really in the low mass side of things, because there's a rich chemistry throughout. And we can actually see the progression of sun-like stars, disks, and planets. And so this is really where my interest lies, is trying to understand how these complex organics are being connected through all these scales. So just to kind of go over this in a little more detail, my background slide is actually the molecular cloud that I study quite a bit. This is Taurus. In this molecular cloud, you have filament-like structures. This is a real image from Herschel. This is a far infrared. This green is the different filaments within the molecular cloud. And my interest, as I mentioned before, is in the starless and dynamically evolved pre-stellar cores that will eventually collapse. And these are little orange blobs were taken with the ALMA telescope and show what they actually look like within the filament. And once they do collapse, they'll form a protostar. So this is an image from JWST. This is, again, in the infrared. And you can see that jets and kind of outflows have cleared away this material and lit up kind of the cavity here. Once your protostar then evolves even more, you get a protoplanetary disk. So this, again, is also a real image. This is from the ALMA telescope as well, but this is submillimeter dust, where you have gaps and rings where people think planets are forming or continuing to form. And all of this, right, is eventually to get us to some mature planetary system, kind of like our own, where you have moons, comets, asteroids, and things like this. And so the big question that I have is trying to connect all of these things together. You know, how did we get here? What kind of chemistry is from one stage to the other? Are, you know, the molecules that we detect early on important for the next stages of star and planet formation? And so these are all the questions that have really driven my research. And actually at each of these stages, we see COMs, these complex organic molecules. So comets, for example, this is our acetaldehyde, which is that molecule observed that I was showing earlier with the green appley smell. Each row is a different comet, and this is showing the detections of that molecule here for different comets. And even in protoplanetary disks, there have been complex molecules detected. This is dimethyl ether detected towards this higher mass disk here with ALMA. And even in protostars, there's lots of interesting molecules. And here, for example, is glycoaldehyde, which I mentioned earlier. Now, this in particular is a really cool molecule and interesting prebiotically. And just to kind of drive this point home further, that indeed there is this connection with prebiotic chemistry, there is this RNA world scenario, which suggests that early life forms relied solely on RNA to store genetic information to catalyze chemical reactions. This complicated figure I just want to show you is each box is a molecule important for this RNA world scenario. the boxes that are solidly outlined have been detected in space already, which is pretty cool. And glycoaldehyde is one of them. And so just to kind of show you again that, again, these are not signs of life, but they are the building blocks, right, to life.
So outside in the Solar Museum out here, there's a little piece of meteorite.
Yes.
Have you read the little placards on it?
Some of them.
One of them says they cut it open and identified amino acids
Yes.
in a meteorite
Yes.
coming across the galaxy
Yes.
into our solar.
Yeah.
Where did it come
From these dark clouds, guys. That's what I'm saying. But like to show you, but for real, but to show you evidence of this, do you have a question before I move on?
Dotted lines is indicating a molecule of interest that we haven't detected yet. Is that correct?
The dashed ones.
Yeah.
Yeah. That we would like to try to follow up with. Yeah. But yeah, so the whole point here is like there is evidence to suggest if you actually look at these stages, right? So this is a protostar. And if you look at the abundances, so how much of that molecule is in this object, which is on the y-axis, and it's normalized to methanol for some different regions, which is one of the smallest comms, basically because it can survive the disformation process and it's a grain surface produced molecule. But anyway, so on the y-axis is different abundances of complex organic molecules in this protostar, compared to those same molecules, but now detected in a comet. So this is 67P. And you could do this also with meteorites, for example, but I'm showing you for the comet 67P. And you can see there's a very, very tight correlation here between the abundances, that does not have to be the case. There could have been a lot of different reprocessing or things going on. And so what scientists like myself think is that this is really strong evidence to suggest that these molecules and the abundances of these building blocks, right, of larger things are really set earlier in the dark cloud stage, in the pre-stellar core stage, because they don't really change much as you go, because methanol was really formed in this earliest stage on the ices, and we kind of continue to see similar abundances of these molecules throughout. Now, Maria, who is the lead author of this paper, we actually got together, and just to kind of give you an idea of work that I did in these last few minutes, next to this protostar, there's actually a pre-stellar core. So a core where there's no star formation happening. And nobody had really investigated the inventory of these complex organics. So what Maria and I did was we used the Arizona 12-meter dish and this telescope in Spain called the ABES 40-meter. And we wanted to go look for similar type molecules that were observed in these protostars in order to really test whether or not indeed these ingredients for life were in the natal cloud environment before they were in the protostars. So that's what we did. Here's our spectra. These are my fun, again, fingerprints of molecules. We detect lots of different types of methanol, this acetaldehyde again, and then dimethyl ether, which is that same big 9-atom molecule that was detected in that protoplanetary disk. And what we find, big punchline, is very similar abundances. So this is basically that same plot, but just in a bar graph format now, where you have abundance with respect to methanol on the y-axis, and these are all the different types of complex organic molecules. And so this is just showing that not only for the protostars themselves, but now for the pre-stellar core, the natal cloud, we also see very, very similar abundances, really driving home the point that the complex chemistry is really set in the pre-stellar core phase and can affect the later stages of star and planet formation, and perhaps deliver some of this material later to forming solar systems.
So is this true even back if you, JWST is looking back in time to 200 million years after?
That's a good question. So people have tried to do this in different environments. This is just within our own Milky Way for now. Yeah.
Distance could be a problem. This could be an issue.
It could. Well, more so the
Maybe it's a,
age or like the elemental abundance ratios or a metallicity it's called. But people are finding that even in different environments, for example, the small and large Magellanic Clouds, which are like our dwarf galaxies, they're finding very similar results as this actually. Yeah.
So going back to that, and you can leave it on this slide, but
Yeah.
that slide you had about the molecules that are prebiotic, and
Yeah.
some are solid that you found, and some are dashed that you haven't found. And I suppose this is coming out of your lab and theoretical studies, but does that allow you to put bounds on the relative abundance of these things that you haven't found?
Yeah.
And for the things that you have found, and maybe this is that one graph that went way up, would you expect to find these other things with more sensitive instruments?
Yeah.
As opposed to, they're probably not there because, you know, the bounds that we can put on are like orders of magnitude less than what we've seen.
There's both of that actually. So one kind of fun example is glycine, kind of the simplest amino acid, and we should have seen it by now in terms of like the sensitivities that we've reached, and how also because you have to think about how bright it's expected to be given the physics of that molecule in the submillimeter band, and it should be very bright, but we don't see it. So we have a very tight limit on what it could be. I think that there is a glycine here with the upper limit, maybe not. Oh yeah, here, glycine.
Okay.
So
Yes.
it's an upper limit, so it's way down compared to here. But again, they did detect it in 67P, but the errors are really big for a number of reasons, which we can get into later. But
So the follow-up on that is related to a question I asked a while back about how do these molecules form, and whether or not the theoretical studies say that if you're trying to make glycine, it's got to form on a planetary surface as opposed to interstellar space. And, you know, does that account for some of the dashed lines, or is that an area of active study or not?
it's very active.
Okay.
Yeah. Yeah.
Okay.
Yeah. No, that's great. All great questions. It's trying to understand which molecules would form and why in certain environments versus the other. That's the whole field of astrochemistry. And it's very exciting because it's relatively new, especially now that we have the capabilities to actually see these molecules in detail. So one of the things that I'm doing next as a teaser for like, what are you doing next? Or it's great to get these, ideas of how much in general is along the line of sight, but we really want to understand where and the distribution. So I have lots of follow-up observations with ALMA, for example. This is a different molecule. This is HC3N, but we're now mapping it so we get an idea of the spatial distribution in both the core of this object and in the protostars. And so we'll be able to better disentangle where things are to understand the physical conditions that we can then put into our models and see if we can get a better idea of like why certain molecules are where, and also how they might be incorporated into the next stages and inherited and things like this. So
actually, I want to ask a fun question.
Okay.
As opposed to the other ones. So and this is a sensitivity question as well, but I think it's fun. If the Earth blew up right now,
yeah.
The Earth has a lot of chemistry on it, right?
Yeah.
So how far away could, with our current telescopes, imagine that we had those telescopes somewhere not Earth. What could we see, the chemistry that was associated with Earth, glycine, you pick for an example.
Oh yeah.
Any notion, is this 10 light years away? Is it 1 light year away? Is it like hundreds?
Oof.
Do you have any notion of that?
This is where it's very difficult because we can't even see on an Earth-like planet, like an exoplanet, like measure the atmosphere like methane.
Yeah. Okay.
So it would be really, really difficult, I think.
So the rationale for the question was if some of the chemistry is formed on planetary
Yeah.
surfaces and planets get recycled or whatever.
Yeah.
Then is any fraction, and it sounds like the answer is that
Well,
that
no, it
mechanism
could be,
wouldn't show up, you wouldn't see
but
it.
it
wouldn't-
not really telescope wise, but say that material gets ejected and comes on a parabolic orbit and gets thrown into some other solar system nearby. I mean, we have observations of these interstellar comets coming into our own solar system, right? So 3 Atlas, right, or the Oumuamua, or these things that are people now know are from other solar systems because they have different ratios of different molecules, and so they must have formed in a colder environment or a hotter environment or something, and they're coming into our solar system, and they have, you know,
Yeah, so
rich molecules.
So that's the material coming to us.
Material, yeah.
Where we can see it because,
Yeah.
you know, 3i Atlas is much closer than stars.
Exactly.
Right. Okay. Yeah, no, it was a kind of a fun question. Because,
No,
you
it's
know,
a
what-
good thought experiment for sure. Yeah. Yeah.
What is the, from an instrumentation standpoint,
Mhm.
is resolution really what you need to get more, to kind of take the next steps here? Or at some point you run into the limitations of whatever instruments you have.
Yeah.
Well, is that the driver, resolution?
It depends on it depends on what you're going for. If you want to see a planet in another solar system, then you want resolution. And so actually they're building what's called the next generation very large array. So next generation of that contact dishes. And it's going to expand outside of New Mexico into Mexico, Texas. It's going to be really, all these dishes are going to be really far spread apart. And what that means is the inverse of your field of view. So then you can see very, very, very fine detail. And so people think you can actually see planets and forming disks and stuff at this. So people are pushing towards this resolution, but you also do need the sensitivity so that it doesn't take you 100 years to
To get
see
to
these.
how much surface area you can do.
Yeah, if you ask an astronomer what they want, sensitivity, bandwidth, so that you can get all these molecules, or angular resolution, they're going to say all, please. But
That's somewhere of the 5,000 exoplanets that they've identified.
yeah,
That they are also identifying that there's water or some other.
yes.
So that's true.
Yeah, so for example, like JWST, this is my backup slide about dimethyl ether, right? So I guess this one doesn't have water, but they have methane and CO2. But again, I want you all to look at the wavelength of light. This is an exoplanet, and it's an infrared. So you know what that means? Overlapping modes. So it's really, really hard to tell that this molecule is this molecule. And so when people were claiming the dimethyl sulfide, they were like, oh yeah, its mode is like overlapping with CO2. And anyway, so this is what I show if people have more interest in the dimethyl sulfide. But yeah, so there is claim they do this transit spectroscopy method where they can identify different molecules. But it's really it's really tough to do. I mean, again, this is the data, the white, and the model is the blue. So take also that with what you will.
What instrument
does the identification of the molecule? I mean, this is not something you could do with your eye, is it?
No, so what they do is
Software?
it's a software, and what they have to do is there's laboratory spectra. So they take ices or take gases in the lab, and they measure that and where it will show up, and then they use the laboratory data and they make models. And so they put in their, oh, what would my model look like if I had CO2 and methane? And then they say, oh, it fit the data. So what they're doing is they're making models and trying to fit it to the data, not directly assigning.
Oh, wow.
So it's, anyway, I'm just saying. Yeah.
Guess I'll wait for this. I mentioned the Atlas 3 and
Yeah.
Oumuamua. I'm sure you train telescopes on them to get
Yes.
air chemistry.
Yes.
Anything remarkable,
Ye-
emerged from that?
Yeah. I wonder if I have a backup slide. On the comet stuff. I think it's not, was it in this one? Oh, yes, I do. This is 2I Borisov, which is also another interstellar comet. And this is again maps from ALMA. What's really cool about this is that you have different molecules. So for example, they had HCN, which is this nitrogen bearing, which was that first molecule in that sequence of RNA that I was showing. And it's very similar to that of the comets in our own solar system. But what was really cool is that the CO abundance was among the highest observed in any comet. And so they think that it formed in a different type of environment than our own solar system, one that was much more CO rich, and maybe in like the cold outer regions of a disk, like, you know, further away, like Kuiper Belt compared to ones closer to us. So anyway, this was a fun one that I just have a backup slide on. But yeah. Okay, well, thank you all for your questions. I am like at the end of my talk, so I'm happy to answer more. Like I said, I have a lot more fun things going on. I'll leave my email up here if you want to contact me or ask me any other questions. I hope I've convinced you all that astrochemistry is really cool. It's an interdisciplinary field, and submillimeter and millimeter radio telescopes are the most powerful instruments that let astrochemists like myself study the rotational spectra of interstellar molecules in high detail so we can get accurate measurements of the fingerprints of these molecules. And most of the molecules have been detected from radio observations. And there's a rich inventory of what are known as these complex organic molecules that have been detected in virtually all stages of low mass star formation. And studying that is really the best place that we can trace this history of figuring out where these molecules are in stars and planets like our own sun and solar system. And my own work has really demonstrated that these complex molecules are seeded early on in the star and planet formation process and likely inherited to the next stages in disks and comets, etc. And so I have lots more ongoing observations. I didn't have time to really show you the Green Bank observations, but I have a whole large program there that's going to study these comms as well in more depth spectrally. So I'm happy to take more questions if you want, but I won't keep you here for longer than needed. So thank you all.
Where do you get your where do you get your grants from?
My grants?
Yeah, you have grants to do these things, I think.
Yeah, so NRAO is funded through NSF, for example. So NSF funding, also NASA funding. So James, the JWST, if you get observations on that, you can get money. ALMA has, for example, a way to get a support for students. So those are the two big ones, NSF and NASA. So keep telling your representatives that we need to fund science.
All right, just a quick,
I know, I realized, yeah.
just a quick survey now. Who thinks radio telescopes are now the best? Yeah, you did good. Yeah, I just don't see it, right?
It can make pretty pictures too.
Well, two things, Dr. Scibelli. So I think we may have actually recorded this. We're thinking,
Oh no,
our guy is in Japan.
somebody is recording.
All right, good.
Like. Okay.
That means we're probably still recording. So that's part one. And part two is we wanted to give you this this coveted past corky cup for caliente items. So woo.
Yeah.
Very few of these are given out. So
Wow.
anyway, that's for you.
Awesome. Well,
Thanks.
it's been really fun. You guys asked the best questions.
Oh, good,
so
good. I'm glad.
This is
All right.
great. Yeah.
Excellent. Thanks so much. Thanks again.
Thank you. There's a question online.
Question from the online thing. Yeah, Marshall Faintish. Is anyone looking for interstellar non-hydrogen, not non-hydrocarbon molecules that might form non-organic forms of life?
Yeah, that's a great question. I think
He's talking about viruses, but continue.
Yeah, I mean, we'll look for, yeah, if somebody gives us the spectra, we can go look for it. I mean, there's a lot of interest, for example, in Titan's atmosphere because they have these liquid methane oceans, and people think that maybe like nitrogen-bearing life instead of carbon-based life forms could arise on this or something. So there is interest in like the forgetting hydrogen and focusing on the nitrogen. So there is interest in that. Usually I think astronomers, this is the case, right? When you think about habitable, like zones of habitability, right? For exoplanets, like if you're in your habitable zone, we just base that off of liquid water, but like there could be liquid something else that supports life, but we don't know any better. So you have to start with your assumption of one. so yeah. But good question.
What is your ratio unknown?
I mean, there's a lot of molecules out there. If you ask a chemist, but
So we have a lot of unknowns and then
yeah.
proportionally which one, is it
Well, I guess it depends on probably like the number of atom molecules. So I think we're kind of probably reaching a good number towards the low, like 3 atom, 5 atom molecules. But like when you get up to larger and larger molecules, we haven't passed, what is it, 13 or something? If we look at this, there's only a few 13 plus molecules. So
but you think the unknowns are us?
the unknowns are definitely a lot larger. If you ask a chemist or biologist their list of molecules for their things like this. I'm not a trained chemist or biologist, so but for astronomers, it's a lot. Yeah. The difficulty is really we just need people in the lab to do the spectra for us, yeah. And it could be somebody's whole PhD. It takes a lot of time. Yeah. Yeah, of course. Thanks for your question. Yeah.
Specific about N2 that makes it hard to detect. I know, and
Yeah. So for example, yeah, N2, I think it is on there, no? Yeah. Oh, okay, yeah. But some of these molecules, H2, for example,
you have N2. Oh, I'm sorry. I wasn't looking at the right column of 2 atoms. I missed it.
yeah, so
My bad.
some of these molecules are actually you can't detect in radio or because for H2, for example, you have 2 identical hydrogen. It doesn't have a dipole moment, and so it can only be observed actually from its magnetic dipole moment in the infrared, and that's at like 400 degrees above Kelvin. So if we want to measure like the hydrogen in whole dense clouds, we can't directly detect H2. So that's why people use carbon monoxide, for example. So there are some molecules that is really hard to detect in radio because of their structure and their symmetry.
It would be
So-
interesting to map this against average signal noise ratio per.
True, that's true. Yeah. There's this paper, McGuire 2022. He has lots of different that's where I got a lot of my graphs from, but he has other graphs in there comparing these molecules to, I don't know, other bar graphs, other types of graphs to see like trends and comparing like which molecules are in which type of object versus another type of object. So if you're interested in that, you could check that out. Hey, nice to see you.
Agents of styles that what molecules we see because kind of this on the chart of the Nash lines versus
Yeah.
solid. that some of the dash lines looked a little more complex. So
Mm.
like, I mean, besides if like all the planets take up the molecules, would your like with older stars possibly have like more of the complex molecules that we haven't done that yet?
Yeah, that's a good question. I think it that all of these things are important and interplay with each other, and so that's what makes it so complicated. I think this is actually just any detection in space, so it's not by certain. It's misleading. It's not from this source in particular. It's just if it's been detected in space. Yeah, but again, some of these like what's 20 is glycine, I think, which where is it? Up here. Again, it's not that complex. And so people are like, we should form it. It's one of the simplest ones. But we just don't see it. And people have been trying to detect it in a bunch of different objects and still haven't. So, yeah.
Have you ever detected a signature of some molecule and haven't been able to identify, you know,
Yes.
that happens?
Yeah. So when I was showing,
So those unknown, that's a molecule that they hope to detect but haven't detected. Feeding backwards, have you detected a signature of some form of molecule that you can't identify what it is? Well, then how would you make the model?
but what do you, so like for here, for example, these are clearly like lines, but we can't assign them anything yet because we don't have the rotational information from lab. So
That's an area of effort.
yes.
Try to identify what they are.
Yeah, there's a whole line of people that are trying to detect new molecules this way, which is
And then we-
important. Yeah, there are ways to figure out if you have enough bandwidth, because they follow like a pattern. You can do like the calculations to try to figure out what that molecule is, and then you go to the lab to confirm it. But yeah.
Calculations for that, right.
Okay, cool.
What we're doing about my iPhone.
We're gonna be here all night. Yeah, keep going.
I know. Well, I mean, yeah, any other questions? But I'm glad that everyone was so interested.
It's a sign of great speaking.
Good, good. Good.
All right, thanks so much. Appreciate it again.
Yeah, thank everybody. Thanks for listening.